You see?
This money already knows. That's why I said tell you his mindset.
Hey, so let's go home for teacher, right?
Masuk deh.
I'm gonna be late for 10 minutes, guys.
Serapnya budaya kan dari Cina.
Aduh.
Hey, you know, my dad went to Chinese embassy in Mauritius. You know what time it open? Open at 8, close at 11.
That's so fun.
Yeah. My dad's like, yeah, you tell me go embassy, open at 8, close at 11. I'm like, yeah, where's my petrol money?
Why so fast though?
I don't know. No, only the visa section closed that fast. Like the other is normal. But for visa, bro, open at 8,
Yeah.
close at 11. Like, bro, what the fuck?
Yeah. 8, 9, 10, couple hours.
So stupid, man. So stupid.
Why is he so small?
CD now.
Salah nama anak yang bikin orang gemetar.
Ini tuh.
Sini tau. Kalau itu lu tau nggak dulu kayak
Shibai.
pas Natal kan ada Santa Claus sama satu lagi yang bawa kaki.
You get out. You get out, I sit on the spot.
Dulu gua di gitu.
You
bisa
main
sport Bom bebo.
Oh.
Dulu pas Natal, pas masih kecil, if you like healthy, like your grandmother, your mom, your dad, like told you, like a black guy will like take
Black guy?
Yeah, you don't you, bro. Not you, like painted black.
Oh, it's the Grinch.
Yeah, why not green? Why not orange? Why paint black?
But
Why can't paint
personally,
orange?
I've seen it. I've seen the guy.
Why you see the black guy?
Yeah.
You see him paint the black?
Yeah.
Yeah, don't paint the black on you.
First April, right? First April.
I want, you know, we have vocab quiz, right?
Yeah.
And then in the like idioms part, there's like usual suspect.
Yeah.
Jamal broke into house because he's broke.
Jamal.
Hey, now you go home, yeah?
Yeah, already 2 minutes past. You know, in German they say it's only very late, right? Not respect time, let's go.
Kalau lu main begini efek.
Tapi kayaknya di Jerman kereta aja telat mulu dah.
Bom, get out, bom, or I break it, bom. I break it, bom.
Tahu kalau Jepang ya?
Kalau Jepang ya, soalnya
Kayaknya Jerman udah biasa soalnya.
Pak Leo.
Three, two, one.
Dapatnya rupiah atau euro?
Kenapa?
Lu kalau di Jerman main begini efek, dapatnya rupiah atau euro?
Mati lu digoreng. Tiba-tiba lu jadi wurs. Wurs lu tiba-tiba.
flash.
Udah lo tiba-tiba udah di stall pinggir jalan gitu udah diapit roti kan. Di sini orang mau nangkep masih kayak najis. Ya apa itu kan? Kalau sana, wow, kritik. Langsung giling jadi wurs. Sampai itu.
Jatuh. Habis apa?
Harus dipijit.
Habis foto Roblox biar buka voice chat.
Oh iya, serius.
Lo tadi di English tadi. Gue main brand roll, siapa yang mau brand roll? Nah, katanya Michael mau cari jodoh di apa di fishing itu ya?
Astaga Michael.
Michael.
Lu cari jodoh anak 12 tahun ke bawah.
Itu udah jadi
Mending panggil Pak Leo. Gendong ya. Mau Michael apa sih punyanya apa sih?
Itu OCD itu.
Kau apa?
Oh iya.
Kau?
OCD. ADHD whatever.
Hah?
Yeah, it's OCD.
What is ADHD?
No.
Anak dan high definition.
Gua kalau pulang, masa gak ada sih?
Kok gagal dulu 4K?
Salah satu lah, gua salah satu lah.
What's the
Hah?
Beli satu ya, gue beli satu.
man?
Ya. You know, he's the dean, so he can set every role.
Mike,
33
ADHD kalau koneksi internetnya lebih bagus bisa jadi 4K atau enggak?
Sorry.
itu kayak accuracy and precision.
AD 4K.
Good morning. Good afternoon. Don't pizza. Flash. Yeah,
Oh iya, snow chain, snow chain. Ya.
Apa sih?
Kasih QR itu ya, KTP tujuan.
Apa? Kan bikin sejauh.
Kasih QR KTP tujuan.
Bisa gitu siang itu.
Bisa scan. Dari ibu fotografi ini, tapi kita berpindah lagi percaya. Ya itu apa? Black History Month.
Wah, mampus. Volume hari ini bukan.
Si 10.
Wah, susah.
What is that?
So, what I want to go through today is the concept of motor sizing. Now, this is in your Google Classroom, by the way, so you can pull it up.
Yeah.
So this topic of motor sizing is kind of practical, and this kind of provides a transition toward, usually mechatronic system design is on the 5th semester, and so this provides a transition toward that design, in which you will exercise a lot of the machine design topics that we discussed all semester long, right? Now, this might belong more toward electrical drive rather than machine design, but I think the concept of torque and RPM relates a lot with what we've discussed so far, right? Gears, belts, and chain. By the way, why is there so few people today?
Go home.
Okay, this will be quizzed. You know that, right? Anyways, so again, the reason we want to talk about motor sizing because it relates a lot with the concept of torque versus RPM, in which we manipulate them using gears, belts, and chain. And so the topic of motor sizing and sizing your power transmission is kind of correlated. So in a typical situation of the mechatronic system design course, you are about to design a mobile robot, okay, that is going to accelerate and it's going to stop, okay? And so back and forth. If we draw the velocity profile over time or over distance, whichever, okay? I'm just going to draw it over time. We're going to accelerate from 0 up to a point where you have a cruising speed or a steady state speed. And then we're going to go on that speed for some time. And then before stopping, you're going to decelerate. Okay, so this is called a velocity profile. And if you want to size your motor for a certain mass, you are going to have to decide the velocity profile that you want to fulfill. For example, what is the acceleration time that you're going to aim for and how fast? So for example, this is 2 meters per second is what you're aiming for, and I'm going to achieve that in 1 second. Keep things simple, right? So my acceleration is 2 meters per second divided by 1, which is 2 meters per second squared. If I want to achieve this in 0.5 seconds, then my acceleration is 4, right? So that's what acceleration means. Yeah, for the sake of it, let's make it 0.5, and this is going to be 4 during that period. And then here, what is the acceleration? 0. So the velocity is 2 meters per second constant. And then here is what is called the deceleration period, and whatever, 0.5 to make it symmetrical. Now, many times the motor resistance alone is enough to provide for this, even though it might not. In the case of electric vehicle, then this is where regenerative braking comes in. But then you might need an extra friction on the brake pad if you're stopping in a much faster way. In the case of mobile robot, because the mass is so small, oftentimes the motor friction alone kind of provides for that. Okay? So here, acceleration is negative 4 meters per second squared. But the motor is doing the most work when the acceleration, right? What is the job of the motor here? Acceleration, right? So this is acceleration, and here, what is the motor doing? But it's not going to do that with 0 torque, right? It still needs to exert something to overcome friction, right? So we have what we're going to call it rolling resistance, because friction is a concept where you have no motion, and then you have motion that is static friction, kinetic friction. Either way, we actually have rubbing against two surfaces. Rolling resistance is different. Rolling resistance comes from the fact that a wheel and tire, okay, this is a tire, as it rolls, this thing actually got compressed because of the weight. And this compression does create some work, right? So I'm gonna draw it a bit extreme. So if this is the wheel, so you have some flattened, right? So this distance and this distance is different. So if this is the, let's call it B, okay? If I call this B, B prime is shorter, right? So B prime over B is about, say, 90%. So you have some compression going. What happens as you roll on this tire? This point is going to be lifted off the surface, right? So the next moment here, this point will now be here as it rolls. But this point, I'm going to draw it with a different color. So the blue dot is now here, and the red dot is now here, right?
Yeah.
So if you are one of these dots, what do you experience? As you roll very fast, well, not very fast, but fast, right? If you are the blue dot, what do you experience? You experience compression and expansion. Compression and expansion. Same thing with the red dot. So all throughout this tire, the effort to roll is actually the effort to do that, right? Think of yourself as compressing the tire 10%, and you have to keep doing that. Is there an effort needed? Yes, something, right? Not zero. The closer this number to 1, then the less rolling resistance there is. So if this is not rubber, but like a steel piece, a solid steel piece, the rolling resistance is actually very small, because the deflection is nothing. But that's just not practical, right? To have a solid steel tire. Okay? So for practical purposes, we need friction, we need, compliance. So as a result, you do have what is called a rolling resistance. Now, this rolling resistance then depends on how stiff your tire is, the material it's made of, the surface interaction with the asphalt. It's complicated, but there is something. And usually, it is a multiple of the velocity. Okay? So you can research rolling resistance, but this is something, but in relation to acceleration, this is nothing, of course. So you have wind resistance, you have rolling resistance. The wind resistance is even small in low speed. So you have wind resistance, and then you have rolling resistance. But the force to accelerate is much, much bigger than the force to overcome rolling resistance or the force to overcome wind resistance, or in other words, drag. Therefore, the driving variable to calculate your motor size is, right, these two factors, because the acceleration dominates. The acceleration, the force to accelerate dominates the motor size. Therefore, it comes down to, right, decide on the velocity profile, target cruise velocity, and the time to reach cruise velocity from rest. This gives you the acceleration needed. So that's the first step. The first step is to decide how fast am I going to accelerate. And pretty much that's kind of engine sizing too for cars. I mean, performance is acceleration. because that is the hardest part of driving a car. I mean, cruising is nothing, right? So this gives you the first variable you need. And this is kind of, you set it. What do you want it to be? Okay? And then you calculate the linear force needed to accelerate and rolling friction that is going to, you are going to overcome. Because even though this is still slow speed, you do have rolling resistance. Calculate the torque at the wheel based on wheel radius and the RPM at the wheel based on cruise velocity. Why don't you take out your calculator? Because I don't have a precise number to work with, so we're just going to come up with something as we go. Now, we have been talking about mobile robot, but in the case of like a mixer, because we're talking about motor sizing in the bigger picture, like any motor sizing, then say if you are mixing, these mixers, right? Dough mixers, bread mixers, adonan, right? And see, if you mix it, then you need a certain torque. So then you're going to start at 3. We start at 1 because the context I gave was mobile robot. But if you already know the torque, then motor sizing starts there. And really, this is the crucial step, is the torque and the RPM. Should have right there. So, torque and RPM at the wheel based on cruise velocity. So, that's the power. Torque times RPM in radians per second is power. Remember your chain problem, right?
Yeah.
So power is torque times RPM. And remember to do it with the proper units though. But remember, if I say, give me a motor with 10 Newton meter torque. Any motor can give 10 Newton meter torque. Why? If you ask me, if you just give me this requirement, okay, I need 10 Newton meter torque to mix the dough. Do you believe it that any motor can give 10 Newton meter torque? Why? The motor this tiny can give you 10 Newton meter torque. Do you believe it? Because I can using gearing, right? I can put some extreme gearing into a tiny motor and it will give me 10 Newton meter of torque. Say I give a gear ratio of 1 to 1,000. But what's the result? If I give you a tiny motor like a 1 watt motor to drive a big torque, what happens?
Bigger chunk.
Huh?
Bigger chunk.
The what?
Bigger chunk.
Need a bigger
Chunk.
chart? What do you mean?
The sizing.
Oh.
No, that's not what I'm talking about. But if I give a very big ratio, a tiny motor can produce 10 Newton meter torque with a huge ratio. But what's the downside? Come on, guys. I mean, by now you're indoctrinated. No, not size.
Reliability.
RPM, right? So can I drive mixing a dough with a tiny motor producing 10 Newton meter torque? The answer is yes. But the RPM will be slow, like slow. Like it rotates like this. Right? I can. Theoretically, I can. That's why when you ask me for a requirement, you cannot just ask me about the torque. Because the requirement to mix this dough is not just the torque. It's the torque at X RPM, right? In order to mix this, I need some speed and torque. So I need 10 Newton meter of torque at, say, 10 RPM. Okay? Then we have a requirement. Because if you just give me torque, I can always produce this torque. I'll give you a tiny motor with a huge gearing. Or if you just give me the RPM, I can always produce that RPM with some gearing that I choose. It's just that the torque will be so small, you cannot even turn anything. Hey, it's 10 RPM. If it's rotating in space, in outer space where there is no friction and no wind resistance and no load. So motor sizing is all about the load and the speed. Okay? Therefore, number 3 says calculate the torque at the wheel based on the wheel radius and the RPM at the wheel. Okay? So the force to accelerate will give you the torque, right? So the torque is force times radius of the wheel. So first you determine I have a what? 3 kilogram mass. 3 kilogram mass times what? 4 meters per second. So I need 7 newtons. 12 newtons. Okay? And my radius of the wheel is what? Say, what, 10 centimeters?
Yeah.
Or 5? Okay, let's say 5. So R equals 0.05 meters. So we have 12 times 0.05. What is it? 0.6? Is it?
Yeah, 0.6.
Okay, 0.6 Newton meter. So that's my torque at the wheel. So torque at the wheel. Again, the question is at what RPM? How do I calculate the RPM requirement for this setup? 3 kilogram, 0.05, 4 meter per second squared. I got my torque. Then what? How do I calculate RPM? What RPM is it? What speed do I pick? This is 0. This is 0.5. This is 1 meter per second. This is 1.5 meter per second. This is 2 meters per second. So what speed?
Cruising speed.
Huh?
The cruising speed.
Why?
It's consistent, I guess.
Who can tell me why? Why? I mean, your answer is correct. I should say that I need a motor that gives me 0.6 Newton per second at the RPM that will give me 2 meters per second. Correct. Why?
Because the question is 2 meters per second.
Huh? Because the motor will be under the most stress, or if I put it in a different sentence, I will ask the motor to give me the most it can give me there.
Yeah.
Okay, you see it? Because power, motor power is torque times RPM. So instantaneously, right before I leave, what is the motor power that I'm using? Zero. Zero, because it's still at rest. RPM is 0. 0.6 times 0 is 0. So as I accelerate, constant torque, the assumption is constant torque. Okay? The reality is not constant torque. You'll see what I mean soon. But I want you to understand the science first. So as you accelerate, it's actually easy. It's easy for the motor until it gets here, because this is where torque times RPM is the maximum. So if I ask the question in reverse, at which point do I size my motor? Well, of course, I will size my motor at the most demanding time, which is here. Okay? Think about the bicycle. When is your leg reaches the maximum? When you max out the gear, you pedal as hard as you can, but not at the beginning. You will feel most tired when you reach your maximum RPM with the maximum torque that you can give with your legs, right? Similarly, your engine does not work the most when you accelerate in a drag race. Think of a drag race. When you first accelerate with your engine, that's not the hardest stress on the engine. The hardest stress is when you are at the maximum speed, pedal to the metal, give it all the torque you can at your maximum speed. That's when your engine is like about to explode. Okay? So again, I want you to understand the science here. Maximum torque at maximum RPM is maximum power. And that's going to determine the power requirement. So, when you choose your motor, you are not choosing load or speed. You're choosing both. And in other words, you are actually choosing power. Okay? So the first step to size your motor is not torque, it's not RPM, it's power. And a lot of students make the mistake when they choose, okay, 3 kilograms, radius, acceleration, and they just pick the torque. And they buy something from Tokopedia that fulfill this and call it done. I bought my motor. Only to find out that the speed does not match this. So the first step in sizing your motor is to calculate torque. Let's continue. This is 2 meters per second. What is the RPM? If velocity is 2 meters per second, what is my omega? What's the relationship between omega and V? V equals omega times R or omega divided by R? Omega R, right? So omega is V divided by R, okay? So 2 divided by 0.05 meters. So my omega is no 400.
40.
40 is it?
Yes.
No.
40, sir. 40.
Oh yeah, 40. Got it. Okay, radians per second. Not degrees, but radians, because you know it's nothing per second. It's radians. Okay. So I got my second number. This is my RPM. This is my torque. So in summary, yeah, RPM convert to radians per second. When I say RPM, I meant omega. Okay. You can convert this to RPM if you want. But in order to calculate my power in watts, I need radians per second. So these are my two magic numbers. In other words, when I say I need my motor, I need something with 0.6 Newton meter at 40 radians per second. This is my motor requirement. And therefore my power is 0.6 times 40, which is 24, is it?
Yes.
I know guys, it's 3 p.m. So 24 watts is my magic number. This is the first number you need because, again, oh, I'm repeating myself by now, right? Not one or the other, it's both. And power concludes that. That's why you measure an engine by a horsepower, not torque, not just maximum speed, right? The engine spec tells you I can produce X torque at X RPM, right? That's how an engine is rated. In other words, horsepower. All right, 24 watts. We got the magic number. Assume transmission losses, then you can assume 24 watts is not 24 watts, right? There is always transmission losses, motor efficiency, add some safety factor. So therefore, you need to adjust for some things. So nominally, or theoretically, you only need 24 watts. But what you really need, so that's the minimum power, so actual power, the 24 watts, you assume some inefficiency. Let's say 0.8 transmission losses, because you're buying this off China and the gears are just messed up. The motor itself has some inefficiency. So let's assume transmission losses of 80%, 20%, and then inefficiency of the motor 10%. This will give us what? Can you divide? Calculators?
33.333.
Okay, so 33.3 watts. This will give me something to overcome this inefficiency. Let's add one more safety factor. What, you want to double it? It's made in China, guys, so let's double it, right? So I'm going to choose maybe 60 watts motor, okay? So add safety factor. Not to mention, don't forget, all your shaft alignment, misalignment will cause all kinds of additional friction, okay? So that's how you kind of first decide the motor power. So add some safety factor to it. This gives you the needed motor size in watts. This is the starting point of your motor size, not torque or RPM in isolation. Okay? Now, there is an additional. Okay. There is an additional consideration though. Is now after you decide on the main power, now we talk about the specific motor torque and RPM because it will still come into play. Because this motor will have to produce still 2 meters per second of speed and 0.6 Newton meter. And it has to span that range, right? So we're still going to now dwell into the torque and RPM. So motor size is watts, not torque or RPM in isolation. Motors come with different torque and RPM combination. They are related. Here's what I'm saying. If the required RPM, say, to achieve this, convert this into RPM, 40 radians per second. Everybody knows how to do it.
There's 2 pi radians in 1 RPM.
There is 2 pi radians in 1 RPM.
2 pi per 60, 40 times 2 pi per 60.
So if omega is 40 radians per second, then RPM is 40
40 divided by 2 pi.
divide or multiply
Divided. Divided.
Who says divide?
Wait.
Who says multiply?
Dari omega to
Divide. Let's multiply.
So we have radians per second multiplied by 1 revolution in as 2 pi radians, right? So what is it?
6.36.
6.36 RPM.
RPS.
Oh, RPS, right. So get RPM multiplied by
Oh, wait. Wait. 381.6.
81.
0.6.
Okay, 382 RPM.
Yeah.
Now, my requirement is 382 RPM. The question is at what torque? Because that a no load RPM is 0 torque. Actual RPM will be lower under load. If the required torque is 1.2 newton-meters, the question is at what RPM? Your stall torque is 0 RPM. So here we come into the motor torque RPM relationship. Enlarge that. Okay. So this is a typical DC motor. This is a typical DC motor torque RPM curve. Okay? This is torque. This is RPM. So you see, this is called the. Let's just pick the red curve. Okay, blue is cold, red is hot. So as the motor gets hot, the torque RPM characteristic also kind of shift. This is called stall torque. Okay, this is the torque it gives at 0 RPM. So if the motor is rotating, if this is rotating, and then don't do this at home, but if you grab the shaft and make it stall, make it stand still, the torque you will feel at your hand is this guy, right? 17.5. Or, in other words, if this motor is starting off the line and accelerates, right? This is why if you drive an EV, that's what's nice about EV is that you get the instant torque at 0 RPM. In fact, it is maximum torque at 0 RPM. And then the torque actually decreases as it goes into the maximum RPM. So this is a typical DC motor characteristics. BLDCs in EV is also very similar. So at this point, yes, you reach 2,800 RPM. At what torque? 0. This is called the no-load speed. Okay? So a motor spec can be very deceiving. If you look up the motor listing in e-commerce, say in Tokopedia, they say this motor has maximum torque of 17.5. Don't you ever think you can run 17.5. Because 17.5 is at 0 RPM. It's useless. You will never experience that. Only at a very brief moment. What you experience is here, right? Somewhere here. Obviously not at 0 RPM. But if the listing, the e-commerce product listing says maximum speed of 2,700, do you think you'll get that? No, because 2,700 is assuming it's rotating in free air with nothing attached to it. And then you just run it and right? So what? Once I attach something to the motor, it's goes into a lower RPM, right? So don't be deceived that when you read a specification, maximum RPM and maximum torque, that you're gonna get both at the same time. No. So know yourself that 17.5 is stall torque and 2700 is a no load speed. So if I need this combination, where do I have to land on the chart? I'm gonna have to land somewhere here, right? You're gonna have to choose a motor that if you draw a straight line between the maximum RPM, i.e. no load speed, zero torque, and maximum torque, zero speed. If you draw a straight line, and then you look at where you are, 0.6 Newton meter, 40 radians per second, or in other words, 382, that I better be here, under the curve. Nangkap ya? Okay, got it? Because then, my motor can overperform what I need. Because these lines represent the combination that I need. And if I'm here, let's say here, if I'm here, then I'm good. Because I'm asking the motor to do something less than what it's capable of at the RPM that it's capable of delivering. So that's how you choose a motor. Then you need these two numbers to get a simplified version of the RPM torque curve and make sure you are below it. Because it is possible that you are here. I'm asking 0.6 is here, it's outside of the curve, or it's here. Then it's not going to happen. Okay? If you're here, here, anywhere here, then it's good. So that's kind of the process of selecting a motor. First, you decide on the watts, put some safety factor on it, and then you have to look at the motor curve and make sure you are below it. Okay? Now I do have an in-class exercise. I'll just make it a homework. So here is some okay, so choose a motor to meet the following requirement in a mobile robot drive design. Mass is 3 kilograms, maximum cruise velocity instead of 2, I put 4, time to reach is 0.5 seconds, easy numbers, right? Radius of the wheel, I almost picked the same number. Okay, determine max torque, max speed of the wheel, select a motor and a drive ratio combination that will deliver the requirement. The reason I put drive ratio is because many motors is incapable of delivering a good amount of torque. They often put a gearbox, right? We talk about this. So oftentimes they come with a gearbox and then a shaft output. So oftentimes you cannot see the actual motor shaft output because it's attached. It's permanently attached to the head, which is basically the gearbox. And if you look at a motor with something in front of it, most likely that's a gearbox. So select a motor and drive ratio combination, include the data sheet, torque RPM curve, or estimated torque RPM curve, the one that we discussed, that straight line, and where you land in the curve during operation.
Sir, the one shown at GDOC, is it like a general curve or
Yeah, but I want you to find an actual motor in the market.
Oh,
Okay.
not the tower curve?
So find an actual motor in the market and download the data sheet and show that you are going to meet that one.
Okay. You did,
A week. I didn't put the deadline when I posted it. No due
Is
date.
it graded
no,
or
no,
not,
no,
sir?
No.
Is it graded, sir?
Yeah.
Michael, no need.
2 days.
But you said a week, sir.
Negotiation go down.
Oh no, not next year.
Next year, okay.
So on week 11:59.
Yes,
Yes.
yes.
Yay.
Close of the year.
Procrastination is the word.
Yeah, exactly.
All right. Now, so that's the exercise. We'll have a quiz on
Next Tuesday.
Friday.
Not faster. What
Spring.
Spring.
Oh,
Sir,
Bring Friday,
This
exercise.
Friday, sir. Holiday for the attendance.
Friday we go.
the QR, sir, for attendance?
I don't think today's schedule is scheduled in
It
that.
is, in the header it is.
Yeah.
Yeah. It's all. No, sir, the quiz is next Tuesday or next Friday, sir?
Friday.
Tuesday.
I think it's Friday.
Oh.
Next Friday.
No, this Friday.
Next
Friday,
Holiday.
Holiday.
So next Tuesday.
Okay.
Spring and water planning, right, sir?
Huh? Spring and motorcycle.
Motorcycle, one motor for the beach.
Fall down.
Real something. Tapi
It is.
Where's my mic?
Yeah, so next Tuesday is the quiz, and next Friday we'll have a review for the exam.
final exam, sir.
The other week.
Wednesday.
Wait, this is Wednesday. It's like week 12 or
Wait a
something.
minute. When is? Oh, it's on the Wednesday,
Yeah.
13th.
Next 2 Wednesdays.
Like
Oh.
the week before ASI.
Wednesday. Tuesday.
No, next 2 Wednesdays.
Okay, Michael.
Ada week before admin. Jumatnya final.
Quiz.
Apa? Cuma apa?
berapa tanggal 12 ya?
Everybody got that?
15.
Tanggal 13 ada ini juga ada atau 19.
Mau bikin lagi sama Pak.
Burns halfway, right? Burns halfway.
Holiday. Terus apa lagi?
Bro, enggak lah, nggak boleh siang.
Jam
Tapi
maghrib
tapi
nggak sih?
saya kos buat
Ya kan semoga, siapa tahu mereka festival. Richard,
Oh.
jadwal lagi keluar kapan ya?
Tahu. Briefing dari sana belum.
Sulit
Lah, jadi semuanya hari pertama dan jam 7 gitu.
Briefing dari admin buat kita aja belum kan?
Biasa gimana? Pamit malam itu atau?
Nggak tahu. Lu baru pertama kali guys ya lu.
Anda kan apa anak dalam admin?
Kenapa sih semua ngomongnya gitu?
Respect.
Ah, respect.
It doesn't matter.
Yeah, I feel like, see, I forgot to bring my lunch box, right?
Pilih.
What's your last one?
There.
Where? Oh, English.
Yeah, my lunch box. Hah?
Yes, bro.
Oh, Inggris.
Kalau admin shift-shiftan kamu hari Jumat nggak bisa pulang.
Makan
Oh,
iya, bang.
saya curi mobil. Hah?
Just go.
Selalu jam 2 siang.
Ya udah kamu nempel. Ini ada HP ketinggalan, Aduh, masukin mesin teleponnya.
Jangan deh.
Masukin mesin teleponnya. Wah, takut dikerjain. Rajin. Ini kalau bingung bisa kayaknya saya wait. Bye.
Tapi jamnya
Thank you so much.
kan waktu itu gua nggak tahu guys.
It's okay.
Kalau tahu mah. Thank you, sir.
Kalau tahu digangguin makin.
Apa?
Kalau tahu makin diganggu.
Enggak lah.
Oh.
Dari situ.
Are you still?
You still need this?
Yeah.
Okay. Ntar hapusin ya.
Ya. Hah? Speed itu RPM-nya.
lagi kan.
Ini harus melalui ini dulu.
Iya.